I'm now going to turn to the first mission presentation, and that one is going to be given by one of the directors of the Perceptual Intelligence mission, which I am one of the co-directors of the Perceptual Intelligence mission. So I'm taking off my director hat and now putting on my PI hat for one of these missions. So, and here I'm really trying to lead by example. So I co-lead this mission with my colleague Josh Tenenbaum and my colleague Vikash Mansinga, Nancy Canwisher, and others. These are among the PIs that are on this mission. And these are some of the students and postdocs that have really been part of this mission. Okay, so this is the Perceptual Intelligence mission. And let me sort of set the stage for this by talking a little bit about autonomous driving. This is something that Josh and I have talked a lot about. I've learned a lot from Josh in doing this. You may have started to think that autonomous driving, you probably heard about this is like 2010. It was always like right around the corner. And then it's always right around the corner. And it's like the last 1% is the hardest. This is like, where's our autonomous cars? Where are the cars picking us up? And when is it going to happen? And then it's no matter, it must be decades away, no matter what Elon Musk says. And now we actually have Waymos, right? I mean, if you go to some cities, there are cars that are starting to drive around, right? So it's really starting to happen. So it took like 15 years, and it's starting to happen a bit. But this is a really quite narrow thing. A lot of industry engineering just to make that one aspect of perception happen. A lot of energy, a lot of dollars to produce something that can actually start to work, but doesn't feel like we've achieved a general understanding of human perception. One of the things that's cool if you have a self-driving car, or not self-driving car, like a full self-driving mode, like in a Tesla, and you go in it, you can sometimes see its internal world model of what it thinks the world is. This is I think, an example from the Waymo. And you can see where it thinks where the other cars are and the people are. And this is sort of a testament to a couple of things that you want to be achieving a world model. So imagine a world where we can have a model of what a human world model might look like. This is, of course, the car's world model that I'm showing you here. We want to have a human world model that perceives the world the same way we do. So in other words, the world model is a model of what's happening in our own machinery as we perceive the world. So the North Star of the Perceptual Intelligence mission is a machine executable model of how human brains construct their internal models of the physical 3D environment. We could probably put it side by side with a model like this and show its similarities and comparisons, at least in this driving situation. But importantly, it should explain the successes and the failures of human perception and prediction and action in any environment, not just a driving environment that's been engineered for over 15 years to just achieve one particular goal. It should explain any possible situation. And it should align with us both on our successes and our failures. That's what a good model should do. And it should have mappable parts, just like I mentioned models in vision have mappable parts for parts of the ventral stream that approximate some of those activities of neurons in the brain. Parts of these models should align to different parts of the human brain, and we should be able to show that how those things align. And that's, again, as a hypothesis of how brains give rise to these mental phenomena of perception. So this is, in a broad sense, our North Star, trying to outlay for you what we imagine when we talk about what we're doing in the Perceptual Intelligence mission. How does humans build these world models, and what are the parts in the brain that contribute to how that works? So just to give you a sense of how the state of the world is in building models of how perception might work, the typical way these systems are done, including some of the ones that I showed you are the current leading models of the ventral stream, they kind of go like this. So you kind of have a real state of the world. You might even simulate the world in some graphic simulator. You connect that to that sort of world here that you can think of like a black box. That world, you connect the inputs to a neural network like a transformer. You take the outputs of that and say, here's what I want the output to be, like I see a dog or I see a house. And then you just turn the crank and you tune the parameters inside this transformer until you get this input-output to align over a large set of data. This is, in a nutshell, how current, quote, AI systems are built, how industry-style models are made. And again, some of these are the leading models of parts of visual processing, so I don't want to say this is a waste of time, but we think it's incomplete in various ways. One thing is it sort of treats the world as a kind of black box and tries to rediscover it by basically brute force data, which requires lots of compute and lots of energy. And this may be, okay. This may be something that we could deal with if we think of that as part of evolution. It's of course challenging for industry to keep scaling that up, and that's where you hear about more and more dollars being spent. But one of the things that's also troublesome about this is it doesn't naturally deal with the so-called corner cases, something that's sort of unexpected, or a world that you haven't been in, or it's a situation you haven't seen. And so what do I mean by a corner case? Well, when you think about a corner case, you might think about, here's a non-corner case. You see a bike driving down a nice, suburban road in daylight on the side of the street, and someone's riding on the bike. A corner case would be someone crossing a dark, busy highway in the middle of the night carrying a bike like this, and this actually led to a death. So that is an example of a corner case situation that a system might have not been expecting. And in this case, that was a major failure. But we do have this general idea that these models, even though they're sort of not quite up to the full understanding of what we think a human mind can do, they had led to, as I've already said, I'm showing this slide again, progress in models of how we model at least parts of the brain, like the ventral visual stream shown here on the left. Okay, so now what our group has been doing in collaboration as part of this mission is we're trying to build models that extend beyond the ventral stream to the whole visual system, both the ventral and the dorsal stream. So here's a brain here, ventral and dorsal stream. And we're trying to take some of the lessons from what we learned in the ventral stream and extend them to the dorsal stream. By the way, those models of the ventral stream have become our leading models of what's happening in the ventral stream and lead to all kinds of interesting application in future science areas that have been, some of those are highlighted on these kind of papers here. So it's been a big success for systems neuroscience to port those models in the ventral stream, and we're imagining doing that for broader areas of the visual system. The models that that in the past we've been using are really based on just 200 milliseconds of brain processing, which we call core visual object recognition. They led to modeling a portion of the visual system, the ventral visual stream, and they are kind of similar to for current industry models. These sort of deep neural network or now transformer AI models. Those were products that started about a decade ago. The next generation of perceptual models we think are going to work in this regime. We call this more like a 4D perception regime, where we might even have sparse data or uncertain data here, being able to detect objects like this in motion in situations like this, which these kind of systems do not do well in. These kind of longer range time scales are what we're after here, and these we think are going to produce scientific models of the entire visual system and beyond. And we also believe next generation of some cognitive AI. So this is pushing us to a new regime of perception beyond this sort of flash 200 millisecond regime, which is where we started. And again, today's industry approach takes a kind of a turn the crank approach. This is an example of video prediction is one of the things that industry's been doing, and this has led to some of the newest generation of models of perceptual processing and even video generation. There's a class of models called VJEPA, which I'm going to tell you about in a minute, produced by Meta, which is, they say VJEPA is a step toward a more grounded understanding of the world so machines can achieve more generalized reasoning and planning. And these are basically turn the data crank on predicting what's going to happen next in video. And then scaling video generation models is a promising path toward building general purpose simulators of the physical world. And so this is a simulated scene here. These are like pirate ships inside a cup of coffee. And that's really quite amazing and really kind of boggles the mind that, wow, these models are really producing those kind of things. Yet they still have these kind of quite dramatic failures where this is not physically what you would expect to happen on this side here. Right, so it's both amazing and something still wrong with it, even after all that data that goes into those kind of training models, these industry-style models. Yet, they are still actually some of the leading models of parts of the visual system, as I'll show you in a minute. So again, glass half full, half empty. These models are still not making human-like predictions. These are some slightly older models here showing that in a kind of a task of predicting where something's going to happen next. And as Nancy Canwisher's lab has shown with others, that these are still not human in predicting perceived contact in situations like these shown here. So the point is these models have gotten better, but they're still not human-like in their behavior. And so now we're trying to take this to say, what's happening in the brain? How do we build the next generation of models? So I'm going to tell you a little bit about work we've done and what's happening in the brain, and then Josh is going to tell you about how the next generation of models are looking. I want to take a moment to pause here to sort of say something I've been saying implicitly that I want to make more explicit. The quest aims to build models that are models of how perception might work. Those models can come from both our own builds, and you'll hear some of that from Josh, but they also can come from industry like VJEPA that I just mentioned here, that come from companies like Meta that are producing models for computer vision or video generation or other applications. So the quest is at some level agnostic to where these models come from to just try to see which one's best aligned. We expect models in the style that Josh is going to talk about are going to be more well aligned, but that's part of the activities that we're we're engaged in is to seeing how these compare. And so we always use industry models as a current baseline to compare when we do things like compare with brains. So let me tell you a little bit about some brain work that we've been doing on the perceptual side, in this case in the dorsal stream, as I said, to try to extend models into the dorsal stream. So you might know, those of you who know our prior work, we worked on the ventral stream, which processes things like objects to say what's out there. Is it a cat, is it a dog, categorization, identification, or to be able to say this is this shape and not this shape. More recently, we've been extending in this mission to be asked things like what are the surface normals, the depth estimation, or location and segmentation, to be able to say more about these objects as 3D objects themselves, not just what category they live in. Things that would be important to things like reaching and grasping, like as, for example, shown here that we can now study in VR. And so one of the stimulus classes that we've been using, I've sort of illustrated here. This is called a shape for motion class. And of course, you guys can all see these shapes in these images, of course, right? I hope the answer is no, because you might be able to see it in that one. But so as soon as I start the motion, you can see those shapes like pop out, right? And you can already instantly perceive a 3D shape, even though you couldn't in a static frame. So this shows you an example of, this is a class of stimuli that would be very challenging for those kind of baseline models that I mentioned, but that we naturally can be able to see. So it's just a kind of example of a failure mode of those older models that we've been after to try to ask, where does the brain, how's the brain solve this kind of thing? To be able to say the surface normals, which are shown here, the depth, or the segmentation. And so this is just one example of an experiment that's been going on in the lab. We first showed that humans, of course, can do this quite well. This is human performance. I don't want you to read this graph other than to say humans can effortlessly match shape across textures, like shown here, with very low level, with very different texture types as you just saw. But we've been doing, when I say we, I mean a number of folks, especially Yoon Bai and Thomas O'Connell, have been leading this work. We've been recording from dorsal areas to ask, how does the brain process these kind of stimuli? We've been comparing with ventral areas, so making neural recordings in monkey brains to do this. One of the things we've learned is that the brain is actually a very good estimate of the shape in both the ventral and the dorsal areas in terms of decoding performance. And one of the things in summary that I'm going to tell you just today that we've learned is some of our best predictor models of what those dorsal neurons are doing when it's processing stimuli that are shown there are actually pretty well explained by some of those VJEPA models that I was saying are both good, and they're both good and bad at the same time. They're sort of our leading models of what's going on with the neurons. That's what these dots here are. This is VJEPA alignment with neurons in the dorsal stream. And this is, again, shape matching accuracy, a sort of AI kind of metric of how you might build those kind of models. But unfortunately, again, these models are still not up to human level performance at the behavioral level. So they're helping us to explain parts of the brain, similar as I showed you ventral stream prior work from our lab, but still not at human level. And so we need a next generation of model that we think are going to match neurons even better in the brain, match other parts of the brain, and also will explain human level performance and tasks like these and others. And so that's where we're headed next. And I'm going to now let Josh come up and tell you a bit more about this next class of models that we're eager to test as he helps direct their building. So Josh, go for it.
Okay. So great. Jim, so inspiring. Every single part from with your director hat, and it's an honor and a pleasure to co-lead this mission with you. There's a third lead of this mission who is Vikash Mansingha. You see the words probabilistic programming there. Vikash is currently on leave from MIT. At MIT, he is a principal research scientist and the leader of the scaling inference platform and one of the world's leaders in probabilistic programming. And I'm going to talk to you a little bit about some of the research that we've been doing, which is taking a sort of a more cognitive science top-down approach, but really building on the scaling inference platform that allows us to build models that we just couldn't build before because they don't look like the same kinds of tech pipeline that industry has been building. But speaking of the relationship between academia and industry, Vikash is on leave right now because he's doing a startup where some of these ideas are already being commercialized back. So the virtuous cycle is one that goes in multiple directions, and it's really exciting to start to see the bidirectional links between the brain, neuroscience, and the AI. Coming from cognitive science, we are struck by the ways that humans, even very young children, build rational world modelers just from the start. You'll hear a lot more about that in the development of intelligence mission in a little bit, but here, just to draw a striking contrast with the long road to autonomous vehicles, as Jim was telling you, huge amounts of progress. The Waymos are really remarkable, and huge amounts of investment, both in dollars, in energy, in data, and really in engineering. And you have a system that just does that one narrow thing, right? In contrast, humans at the same age, they're learning language and learning to get around everywhere else in the world. You can put them behind the wheels of a car. Don't recommend it. It's surely not as safe as a Waymo, but it's really striking how much, just for the first time, a 4-year-old can make sense of the world with these new affordances. And that builds on evolutionarily ancient mechanisms for modeling the world and constructing a model of the world in front of us in our senses. Even brains orders of magnitude smaller than ours, in their more limited Umwelt, do that. So how are we going to engineer that kind of system? Well, the idea is, instead of just having a black box but super powerful function approximator that's trained on the inputs and outputs to the brain, we're building in what we think evolution has built into our brains, namely some kind of a cognitive architecture, a multi-level hierarchical symbolic structure, something like what you have actually inside simulators that are used in game engines as well as robotic simulators. But the idea is, this is inside your own head. It's a model of what's inside your own head. A key part of these simulators, these mental simulators, is that they are probabilistic. That's where the probabilistic program idea comes in. And that allows them to deal with massive kinds of uncertainty. I think many of you, all of you, are familiar with what in machine learning we call the out-of-distribution problem. And whether it's these displays like these random dot textures here, where you can, if you look, you can see an animal moving, right? Or driving at night in the rain, or all these other settings, you know, this crazy headcam data. All of these are not the normal setting, and yet our brains are able to deal with it. Not as well as maybe under ideal circumstances, but our ability to make sense of the world through our perception, to make good guesses and good bets, sometimes and actually quite frequently betting your life on the bets that your perception system enables, is remarkable. And the probabilistic programming machinery that the scaling inference platform allows us to do this, because it combines the power of differentiable programs, end-to-end learning with gradient descent, the neural network stack, basically. It combines that with symbolic languages for abstraction and capturing the structure of the world as we really understand it, and probabilistic inference for making these good guesses and good bets. I'll tell you about just a couple of where our models are, the leading edge. This is from work that Nishad Godaskar recently finished in his PhD, along with George Mateos and others. And this is just an illustration of how probabilistic programming lets you solve effectively the kind of problem that Jim was talking about, seeing just in this case one moving object, a 3D object moving in time against a stationary background, also when you might have ego motion or camera motion. And the system is doing no machine learning here, or no learning. It's just doing pure inference. It says the world consists of little chunks of matter that cohere together into larger blobs, and it's trying to infer from the video data, where is the matter? Where is the independently moving chunks of matter? And it can run extremely efficiently in real time, or faster than real time, just on a single, relatively small GPU. So it's a very different kind of engineering profile than the machine learning-based computer vision systems that industry has been focusing on. Most recently, the team has extended this into settings of like non-rigid objects, like watching a blob of jello, or even more exciting things, as you'll see in a second. This is from work led by Eric Lee and others. And these systems, though they've been developed for computer vision, trying to have a new cognitive AI take on the core problem that Jim was talking about, we are now working together and bringing them into contact with the hard stimuli that we've been studying in brain behavior, these ones that Jim just showed you here, to build systems that can actually see these and other out-of-distribution visual stimuli, as well as the brain and human behavior. We started off just recently by working with an even simpler 2D case. Again, if you look at these images here, you can probably see that there might be one or two objects. We test whether people can see one or two objects by just saying when the red and green dots appear, are they on the same object or different objects? And here you can see our system making these inferences, even with very noisy, sparse data. And again, importantly, we can do the following kind of analysis where we're not just scoring models by how correct they are, but we're looking at the graded performance of people and models, probability of being correct, and the models capture both the successes and the failures. That is, when people, for stimuli, when people find it harder or are less accurate, the models are matched to that. And the sort of leading models for machine learning are basically at chance. They have very, very low correlation here. Most recently, we've been, again, applying them to these stimuli, and you can see here how they're able to, not perfectly, but start to do the segmentation and even to see the 3D shape in motion, even for harder cases like these, where you can see, like on the left, for example, when the movie first starts, it's getting it wrong. It's not seeing it, thinks there's like a hole in the object. But because of probabilistic inference across time, that's quickly filled in, and the system does really quite well. Again, it's near maximal level of performance with enough inference, and that's quite a bit better than state-of-the-art machine learning models. That's where we are in terms of the behavior and brain side, and it's really still very much a work in progress. But just to give a taste of where these things are going, again, they can handle not just rigid objects moving against a background, but something like an animal, like this swan here as it goes down the river. Many other kinds of animals with all the complex rigid articulation and non-rigid motion that they have. And again, even things like, here's the jello blob, seeing the parts of matter and grouping them into a coherent blorbing whole, or very non-rigid cloth, seeing that and grouping those together into coherent chunks of matter. And even a fluid, like the liquid in the wine glass swirling inside. These systems are capable of seeing all that. So that's on the computer vision side. And where we're going next is now studying how the brain is able to perceive all these different kinds of physical matter. And it's far from our full North Star, right? But it's the next step. And by working with these platforms and with our amazing team, we're really excited to take the next few steps and at the progress that the future promises. Okay, thanks.